Alrighty, so I wanted to give you guys a little bit of a supplement with the DTFT. What I want to do for this is just a simple example. It's a poster child example that ends up showing up on some of the homeworks and very often an exam. So please sit through all of this. I know it's not going to be super fun, but it will help you a lot to kind of have extra examples in your head moving forward. All right, so here's a DTFT example. We're going to let xn equal 2 times a Kronecker delta function that's been shifted. And this one's been shifted notably to the left here by 3. And the amplitude of it is just a little bit bigger. We're going to look at an output that's given to us in the form of a recursive equation here. So we call this by a number of different names, but in particular for discrete processing, we call this the difference equation. As you may remember. And what we're going to do is we're going to utilize the DTFT to solve the difference equation. So what we did in some other settings for other courses is we use transformations to, say, turn differential equations into polynomials, right? So before, we might have seen diffeq, right? And we use transforms to make them polynomials that were easier to solve, right? We're going to do a similar thing here. They're going to be rational expressions that we can work with a little bit better. We're going to use the same trick, by the way, later on for the Z transform and things like that. All of these are really related. As we mentioned or will mention in class, the Z transform is kind of a generalization of the DTFT in the same way that the Laplace transform is a generalization of the Fourier transform. So, what happens when we transform our original equation here, this guy, copy that over, and paste it down here again. What happens when we move this into the frequency domain? So use a Fourier transform, in particular the DTFT. We end up with, well, y of n doesn't go anywhere. That's just, by definition, if we take the DTFT of that, it's just y of e to the j omega. But when we do this little shift here, this delay, that actually has an identity for us in our table of identities. And so we can just carry along the constant, and we end up with the same DTFT, but that delay, that shift, actually creates this kind of phase term for us, or phase factor, I should say, of e to the minus j omega. And the number of delays that we have here, say this was minus 2, we would have a 2 or something like that over here. So this amount determines kind of this extra winding that we might do on this guy. All right. For the right-hand side, very much the same. We're just going to end up with the DTFT of the original input. And then for the delay here, same story. It's going to be x e to the minus j omega. And then times that delay element transformed into the Fourier domain. It's just j for omega. It's a little squished in there. Why don't we go ahead and collect some factors, factor out some things that might be useful here. So we have 1 minus a quarter, leaving behind a little phase shift there. And then x e j omega, leave behind 1 minus e to the minus j for omega. So when we put it all together, we can see that there's a couple different directions we could go. We could try to solve out directly for y here, but we're given x to begin with. We're explicitly given, what is x equal to? Well, this is a little bit of a cheat here, having such a nice little function. This is actually an impulse already. It's just shifted and delayed a bit, moved forward in time rather than back. So we're effectively working with an impulse response here already. We'll transform it later on to actually explicitly solve for the impulse response, but for right now, just keep that in the back of our head. Now, if we take this expression and we put it into the DTFT, into the frequency domain, what do we end up with? So 2 Kronecker delta of n plus 3, so xn here is equal to 2 Kronecker delta n plus 3. By the power of the DTFT, we end up with, using our identities, positive 3 j omega times 2. And we can go ahead and substitute this in directly, all right? And what that's going to do for us is now we have just one variable we're really solving for. That's this y, right? That's y in the frequency domain. Everything else is just some kind of function. So if we can rearrange that function into something intelligible that's able to be pushed back through the inverse DTFT easily, maybe through one of our tables, we'll be in really good shape. So let's go ahead and collect things together and see what we're dealing with. We've got now y of ej omega is equal to this 2e positive 3j omega, 1 minus e minus j, it's 4 omega. I know we got the order here wrong, so let's just, it doesn't really matter, but there we go. And 1 minus a quarter e minus j omega. Okay, so we have an identity here that we can use. So recall that a to the n un is a transform pair, oops, not alpha, a less than 1, of course, or for it to converge, 1 over 1 minus a e to the minus j omega. Okay, so I could see where this is going to line up with this guy here. We're still going to have to deal with the stuff upstairs, right? Something's got to be resolved up there. I've got this complicated 2 terms up there, but if we think about it for a minute, it's just a fraction. I can just pull it back apart and distribute that common denominator. So let's do that real quick. We have a rewriting of this guy. This is going to be equal to, now breaking this apart from the top portion into 2 pieces. We're going to distribute this to the 1 and distribute this to the e to the minus j times 4 omega. So in the first place, we have 2e to the 3j omega times this 1 over 1 minus a quarter e to the minus j omega. And then for the second term, we're just going to end up with a cancellation here between these two. And what we have is just minus j omega. So we have 2 e to the minus j omega. And then 1 over 1 minus a quarter e to the j omega, minus j omega, sorry. Already we can see the makings of a solution here because this portion and this portion are essentially just shifting us to the left, and this one just a little bit to the right for the result here, which is expressly coming out of this 1 over 1 minus a quarter e to the minus j omega, and that's going to give us this nice nice kind of polynomial form, if you will, exponential form, excuse me. All right, so using this identity, we can now convert this back to the time domain. And what we end up with is the following. We can just say, using the inverse DTFT in our handy-dandy table. And assuming that we have nice convergence, which we don't really have to assume because A here is equal to 1/4. So we're good on the convergence front. That's no problem. Yn has got to be equal to 2 times 1/4 to the n, un. And then it's delayed, right? It's got this weird delay factor. In this case, our delay is pushing us into the future. We've got a convolution with n plus 3. That's how I like to write it anyway. You can express it how you want. You can put it in there directly. I find this easier because then I know that I need to distribute this to all of my n's. It helps me keep, better record keeping, I suppose. Same thing over here. And actually, I'm going to... I missed my parentheses here. That's what's messing me up. All right, un, again, same function. This time it's going to have a little bit different delay. We're going to have this delta n minus 1 for this part. All right, that's it. That's the solution. We've got our output is this. All right, what does it mean for us exactly? Well, let's consider what we started with. Our input was a delta at n equals minus 3, right? And it had been scaled by 2. And I could almost peel off exactly what's happening with respect to the impulse response because of this bit of information here. We can see that everything's starting at 3 steps in the future. That's fine. But basically, our inherent response, our impulse response, is going to look something like a decay function minus another decaying function. So let's see what happens with that here. Let's ask ourselves, did we learn anything else? About the system. In a sense, we have the impulse response. We just need to extract it from this. So let's ask, what is it? What is the impulse response? We know that, by definition, Yn for an LTI system is equal to xn convolved with hn. So known, missing. Okay? We now have 2 delta n plus 3 convolved with hn here. And we have yn is equal to then 2 times h n plus 3, which means that 1/2 of y convolved with a delay in this direction. Let's actually bring this down here. Sorry about that. Joink. Minus 3. Oops, need an n in there. N minus 3. This is kind of a goofy way to do this, but it helps us see what's really going on here. This is equal to hn plus 3 convolved with delta n minus 3. And since I was able to absorb that delay into the impulse response expression, I can do the same thing again and get back, the thing I'm actually looking for, right? So I kind of did an undo of the functions or the operations that I did originally to x, were x starting as an impulse, right? That's one clever way to use some of these nice looking functions to pull out the impulse response. If you've already got it, work with it. The other thing that we're going to see in the future too is that when we don't have a nice x to work with here, what we'll typically do is look at the ratio of, kind of going back to here, we'll look at the ratio of y to x. And you may remember the identity from 300 or 205, where we had y over x is equal to h, right? In this case, we'll have y ej omega, x ej omega, h ej omega. Once we get this guy, we can just pop it through DTFT, sorry, and recover hn. In this example, I'm just kind of saying, well, it's close enough to an impulse, so I'll just kind of massage it until I get back that impulse that I was looking for. Okay, so coming back down here, let's finish off the expression. We know what yn was. We can just pull this guy down here. We circle all this stuff, copy, paste. And now, with this in mind, I'll just kind of cheat. 1/2 of this convolved with a delta n minus 3. And obviously, this is going to give us something a lot more simple. We're going to have 1/4 n un. And there's no delay, right? Because this guy is going to apply to both terms. Note that when you are multiplying, generally speaking, you wouldn't really distribute a convolution. But we have terms here, right? There's a minus sign in here. So there's 2 separate terms that need to be adjusted by the delay here. The 2 and 1/2 obviously cancel out. We're left with 1/4 n un. And then this guy is convolved now with, we're going 1 step forward and 3 steps, 3 steps forward. So, a lot of delay on that. We're going to have delta n minus 4. And you could rewrite this, of course, as a quarter the n un minus 1/4, 1/4 n minus 4 u of n minus 4. Pretty clearly here we have the same function that's just turned on, and then later on it's turned back off. This is going to be a nice infinite impulse response. We should be able to see that right away from the difference equation that we set up. Right here in our difference equation, we had a recursion, right? So this feedback loop is going to perpetually give us a quarter of what we had from previous. This guy here is just going to act as kind of a finite impulse response element that's getting rid of some of the inputs at a later time. So it's shutting off that input almost entirely. But this feedback mechanism is going to make this an infinite impulse response. I'll call it an echo. Why not? But you can kind of see just from the math here that this is going to continually spit out some kind of output. All right. There we go. This is equal to hn. Pretty straightforward. Not too bad. Now, let's play with this example a little bit further. Let's do one other thing. We first asked ourselves, what is hn? And now we're going to ask ourselves, how could we modify the difference equation by the way, it's no accident that this also would abbreviate to diffeq, because essentially, for all intents and purposes, a difference equation really is just the discrete version of a differential equation. Differential equations, of course, have these differences of delay, but they're infinitesimally small, which is why we represent them as derivatives. So derivatives that occur one infinitesimal thing next to the other one, those are going to be our first derivative. And if we're looking at a second derivative, you can actually think of a second derivative as not just looking at the difference between these two guys, but the change in differences between two. So I could, let me draw this a little bit better. If this is some kind of delta, and this is some kind of delta, then I might be interested in the the change, I would do a delta of delta. We could say the delta of deltas. There we go. The delta of deltas is going to require some double differences, right? So the more that we look at delays in a discrete processing system, the deeper the derivative could be thought of as. So there's a lot of different ways to approach the intuition here, but if this helps, giving a mapping back to the continuous domain, by all means, go for it. So anyway, how could we modify the difference equation? A little side jaunt. To get, oops, buffered, pure exponential impulse response. Well, this is a deeper question. We had kind of this exponential decay here, but it had some funny business going on with respect to this delayed element. We're sort of subtracting off a little bit after some period of time has gone by. Now, the overall result, of course, is still going to be infinite, but what if I wanted a nice, pure exponential, something that was just at 0, it turns on, and then it just decays nice and smoothly, no subtraction, no funny expressions, just a pure exponential decay. Well, the answer to this riddle is I want Hn to look like, more explicitly, this guy. Let's say, i.e., that is to say, this is what I want. All right. Well, if we go back to the difference equation, we had Yn is equal to minus a quarter, sorry. Had the delayed version of the output. And we had over here, all the way back up, minus xn minus 4 right here. Oh, goodness. All right, there we are. Minus xn minus 4. And you can almost bet, because of the delay that we see here and here, that this is the portion that's causing us a problem, that's causing this discontinuity in our decay. So what we can do, if we wanted to get a pure exponential impulse response out of this thing, we could just get rid of this. And this new expression, this new difference equation, would do that for us. So we get rid of those delayed versions, and this is what's left for use, for us. There we go. All right, and we can see that if we put in an impulse for xn, the output should be just this decay function. We go back through all the rigmarole and actually solve this out. So in this one, and we'll talk more about this later, but in this version, we're just placing the poles. And you'll learn more about poles and zeros in particular in 320 if you end up taking that for controls. Controls are really nice for using the complex plane to help define a system in a really easy, mappable way. In this one here, we're just placing our poles in a specific location to help give us that infinite effect, and the zeros would be the ones that were causing this that discontinuity there. Okay, let's go on to another question here. What if we What if we wanted a moving average? Well, this is maybe asking something a little bit completely unrelated to the original, but it's still kind of worthwhile thinking about difference equations and how we might modify them. So we started off with something that looked like yn minus, right, that 1/4, yn minus 1. So there's a couple of problems with this expression right here. The first one is that this is looking at a difference. Oops. Of neighbors. Now they're not exactly neighboring right next to each other, but for all intents and purposes, yeah, it's kind of looking at two nearby samples in time and looking at their difference. What we would probably want to do for a moving average is add all the things together that are near each other and then give them kind of a relative weighting. We also probably would want to avoid any kind of feedback. There are some smoothings that we could do. If we wanted to, say, take something like this and run it across some kind of data set, some kind of time series. I don't know, maybe this is a little too regular to start off with initialization here. There we go, make it a little bit noisier. We're going to run this convolution across here. These guys would just pick up 3 in a row, okay? We might want to do some kind of tapering operation. We may even want something that has kind of an infinite taper to it as a moving average. So you can see here how we might build a finite moving average versus an infinite moving average. So actually our question here is a little ambiguous. We might ask, the person that asked us, do you want a finite one? Do you want it to be infinite? Does it make a difference? It might, right? It might. So let's suppose we want just a simple finite moving average. Oops, not a question mark. We have more questions. That's your job as an engineer, is to keep asking all the questions until we figure out exactly what the customer wants. In this case, they haven't told us everything, right? What if we wanted a moving average? Well, that's not very specific. We could make this into a moving average, I guess. At some point, it's going to stop resembling the thing we started with, but that's okay. We've decided that we wanted a finite moving average, but we didn't say how long we wanted it to be. So we need to decide on a finite number of delay elements that we want to tack in here. And our final form should look like this. And we could do 1 over capital N here. We could do n minus 1 to normalize this real nicely. That way we have n elements, or n delays, n taps. Lots of ways to think about this. Alrighty. Finally, another really vague question, but what happens if we have yn, we take the second delay element here? What would this do? And we left everything else. What if we just left xn minus xn minus 4, whatever it was? We could simplify this and maybe throw this away and ask the same question, but what would happen in general if we just used a delayed version of the thing that's causing the infinite impulse response, a delayed version of the recursion. It sounds kind of cool. Delayed version of the recursion. Sounds like something someone might say in the 80s. I don't know. Let's see here. So fundamentally, everything's going to look kind of the same, except we'd have 1 over 1 minus e to the minus 2 omega j for this guy here. And this doesn't really match our step function formula. From the table. Right, so if you go back and look at your table, you might have a little bit of an issue. So what are some other examples of this? Let's suppose we have h e to the j omega is equal to, let's do something like this. We already have 1 plus 0.3 e to the minus j omega. We'll add in something like that into this guy here. This is sometimes referred to as the system function. Or the transfer function. Either way. So this guy here, I guess I should do this in like purple so we know that it's a note. There we go. The thing we want to think about is what happens when we put in a sinusoid. So we've said all along, and this is just another example of it, but what happens when we put sinusoids into LTI systems? We get sinusoids back out, presumably at the same frequency. Now the phase and the magnitude may change, and that's a good thing for filtering, but fundamentally for an LTI system, a frequency goes in, the same frequency should come out, which is why we have a frequency domain. All right, so when we look at this relationship in the frequency domain for a system process, we have this identity. So we could say that this is equal to the ratio of these two things. And we could suppose, for example, that xn is equal to 8 cosine pi over 5 n plus pi over 3. So the first thing we should ask ourselves, anytime you see a cosine or a sinusoid or something like that as the input to a system, so let's make a little note. Anytime xn is a sinusoid or just a plain old sine or cosine, ask what is the frequency? Because I guarantee you I'm going to give you a problem where I give you some kind of system input, and 9 times out of 10, if it's got a cosine or sinusoid or something like that, you'll be able to just look at it, grab the frequency off of there, and have a really nice hack for how to solve the problem. In this case, we can actually see this if we think, sinusoid, we can spell. Sinusoid of omega goes into the LTI system. We get a sinusoid. Come on, pen. Sinusoid. Omega back out. Say Hn is an eigenfunction. Oh boy. shouldn't be HN, this should be XN. All right. So what we can do here is assess, and we did this in 205 as well, by the way, so you can go review those. But we can assess HEJ omega at omega equals the frequency that we have here, which we can pull right off of this, should be at pi over 5. This is going to give us a nice, clear expression. It's going to be a complex expression, but that's okay. We can pop that into the calculator, or Maple, or whatever. Pi over 5 plus 0.6 e to the minus j pi over 5. And what we'll see is that if we solve this out, HEJ omega at omega equals pi over 5 gives us a phasor, which looks like this. Obviously, this is the angle, this is the magnitude. So we have some kind of loss here, right? We have a little bit of attenuation, and we have a phase shift happening to whatever input signal I have. So now I can solve this out really explicitly. It's quite easy for yn. Yn is just going to be equal to xn. It's going to be, well, we'll write this business here first, times xn. And we'll cover this identity again in class, but whenever you have a sinusoid in, you can cheat and just use h of EJ omega to solve, just like we did in 205. And probably 300 to some extent. In this case, the solution is going to give us an xn, that's supposed to be an arrow, an xn that's equal to 8 times this attenuation factor, 0.6205, and then a phase shift isn't going to be a sinusoid anymore. We're just going to incorporate it directly into the cosine function. So cosine, again, the frequency doesn't change. And we just add this little business to the original value, pi over 3. So using decimals, that's going to give us 0.487 pi, somewhere in that ballpark. And that pretty much does it for what I want to talk about for this video here. Hope this has been helpful. The big thing here is that we have two really fundamental examples, just to summarize. One big example is what happens when I put a sinusoid into some kind of arbitrary system or transfer function, as we may call it. And the answer to that is find the frequency of that sinusoid and apply it to that transfer function and multiply that directly to the input in the time domain, mind you, because at the end of the day, once we assess this guy at a specific value, this is just a constant. So we don't have to even worry anymore about what we were doing in the frequency domain, because it's a constant value for a fixed frequency. If xn is built from a couple different frequencies, and we can kind of parse this out, another trick we can use, here's another note, so extension, I guess from the last, what do we call this, 4? Let's call this one 5, I guess. All right, so extension of 5. If we suppose xn is equal to a sinusoid, come on, there we go, sinusoid omega 1 plus sinusoid Oh man, if I could just not make the same writing mistake multiple times, that'd be great. Omega 2, then we could actually split this up. We could split the effect. For LTI systems, we can always split the input, right? X1 plus X2 into the system gives Y1 plus Y2 into the system, where X1 in gives Y1 out, X2 in gives Y2 out. So we could cheat here. If I have the sum of two sinusoids are totally different frequencies, if I have a finite number of frequencies, right, and I'm adding up over those sinusoids, I could just do H, E, J, omega 1. This is a constant. It's a phasor. Okay, and it's going to go to X, we'll call it X1 of N plus, this is our output, by the way, H at the second phase, or sorry, second frequency, and it's going to make a second phasor attached to the second sinusoid. So this would be up here X1, this would be X2. And I think I have a homework problem that delves into this for you guys, and we'll probably review it at some point before the exam. But really important context to keep in mind is we're dealing with LTI systems here, so anytime you see sinusoids, mark the frequencies that are there and figure out what impact the transfer function is going to have on that input. Right? And most of the time for passive systems, if you don't have any power going into the system, it can't do anything except give you something less than or equal to 1 as a magnitude, and then frequency will very often push your phase around quite a bit. And we'll talk about that many weeks from now when we get to things like the Z transform. Okay, thank you very much for your attention, and hope this was helpful. Have a good one.